Assalamualaikum and good morning, everyone. First of all, I would like to apologize for not being able to attend the presentation in person. As I am currently unwell, I will be presenting from home instead. Today, I will be introducing our topic, sequential logic circuit. Let's go. Before we start, I will introduce our member. So the first one is Umaira Maisara, the second one is me, Muhammad Aiman, and the third one is Muhammad Syakir. So today I will be introducing our topic sequential logic circuit. Unlike combinational circuit, sequential circuit have memory that can store binary data, either 1 or 0. These memory elements called flip-flops are built using logic gate arranged to store and maintain data. They are widely used in counters, registers, and digital clocks, where timing and data storage are important. Thank you.
Okay, I am Muhammad Shaki. Now I want to explain about type of gate. First, this is non-gate latch. In non-gate latch, there are a cross couple. The gate arrangement is similar to non-latch but construct using no gates. However, the normal output Q and inverted output have a reverse position. And the picture at the up here is for non-gate. And this is a figure for a NOR gates. Okay, this is a truth table for NOR gate latch. In this truth table, we have S and R. If S is 0 and R is 0, the output is no change. No change is have no effect of the output, and it can call a hold. And if S is 0 and reset is 1, the output is 1, and it called reset. When S is 1 and R is 0, the output is 0 and become set. Lastly, if S is 1 and reset is 1, the output is invalid. It because the output, both output become 0. And now I'm gonna explain about logic circuit diagram. This is SR flip-flop. SR flip-flop with clock signal labeled as CLK is triggered by PGT. It means that the flip-flop can change the output state only when the clock signal transition from low to high. This is a figure for clock SR flip-flop. The operation of the SR flip-flop with PGT can be summarized in truth table, where the waveform that illustrates the operation of SR flip-flop is given. Okay, this is a truth table for SR flip-flop. SR flip-flop. In this truth table, we have CLK, SR, Q, and Q prime. When S is 0 and R is 0, the output is unchanged or called good. And when S is 0 and R is 1, the output Q is 0. It means reset. And when S is 1 and R is 0, the output Q is 1. And it means set. And lastly, when S is 1 and R is 1, the output Q and Q become 1, which is impossible. It means invalid. Okay, in this slide, it's give a picture. In the left side, it show for a SR flip-flop waveform, and the right side is for symbol SR flip-flop. Now, I will explain about JK flip-flop. JK flip-flop is similar to SR flip-flop, except there is one major difference. When J equals K equals 1, the flip-flop will go to its opposite state instead of becoming invalid state. In figure show JK flip-flop logic circuit and its corresponding truth table is leads in. Okay, this is a truth table for JK flip-flop. When J is 0 and K is 0, the output Q is remaining unchanged and its mean hold. And if J is 0 and K is 1, the output Q is 0 and its mean reset. And when J is 1 and K is 0, the output Q is 1. Its mean set. And when J is 1 and K is 1, the result of the output Q become toggle. Okay, in this slide, it show about JK flip-flop waveform figure. And now I will explain about D flip-flop. D flip-flop is also known as a data type flip-flop because of its ability to store data for a single binary digit. The D flip-flop has only one input in addition to the clock input, which means that the flip-flop output can change when the clock is triggered. This is a figure about D flip-flop. The operation of the D flip-flop with PGT can be summarized in truth table, where the waveform illustrates the operation of D flip-flop is given in figure. Okay, and this is a truth table for D flip-flop. It only have D for the input and CLK, and the output is same Q and Q prime. Okay, when CLK is 1 and D is 0, the output Q is 0. The flip-flop is in reset mode. And when the CLK 1 and D is 1, the output Q is 1. The flip-flop is in set mode. Okay, in this slide, it shows a picture. At the upper side, it shows about D flip-flop with PGT waveform. And the down side, it shows about a symbol of D flip-flop. D flip-flop. D flip-flop can also be construction by using SR and JK flip-flop by addition of an inverter. Inverter is connected so that the R input is always inverse of S, or input will always complementary of K.
My name is Myra Maisara. So today I will be starting my presentation with a clock signal. So what is clock signal? A clock signal is a continuous square wave that alternates between high, which is 1, and low, which is 0. It's used in digital circuits like flip-flops, counters, and microprocessors to synchronize all operations, meaning everything happens in step with the clock. So each full wave from high to low to high again is one clock cycle. So clock signal is divided into two types, which is PGT, positive edge transition, and NGT, negative edge transition. The label T in the figure is labeled as a cycle. So the difference between PGT and NGT on the clock flip-flop can be differentiated by the use of a bubble. The control input will have no effect on Q until the active clock transition occurs. Positive edge triggered the clock signals changes from low 0 to high 1. It's also called the rising edge. And next one is circuits that respond to this positive edge trigger. And the last one, this positive edge trigger is commonly used in flip-flops, counters, and registers. For positive edge trigger, the clock signals changes from low 0 to high 1. It's also called the rising edge. And next one is circuits that respond to this positive edge trigger. And the last one, this positive edge trigger is commonly used in flip-flops, counters, and registers. For negative edge trigger, the clock signal changes from high 1 to low 0, and its uh, other name is falling edge. So the circuits that respond to this are negative edge triggered. Clock flip-flops. So as we learned just now, which is BGT and NGT, there also are clock in flip-flops. So in flip-flop can be designed to respond in two main ways. The first one is level trigger, which responds while the clock is at a certain level. For example, when high level triggered, active when clock equals to 1. When low level trigger, active when clock equals to 0. So the second one is edge trigger. Respond only at the moment the clock changes, which we learned just now two types of clock: positive edge triggered, respond on rising edge; negative edge triggered, respond on falling edge. So next, I will explain about asynchronous counter and synchronous counter that include result and discussion. Okay, first we will go with the asynchronous counter. What is asynchronous counter? So, asynchronous counter is a flip-flop that are connected in such a way that the output of first flip-flop drives into the clock of second flip-flop. And the second one is flip-flop are in the asynchronous counter are not connected simultaneously. And the third one, circuit is simple for more number of states. And the fourth is speed is slow as clock is propagated through number of stages. So this is the design of asynchronous counter in 2-bit, which we have down counter and up counter. So now we will learn how to design asynchronous counter in 2-bit. So the first step is determine the number of flip-flop used. So we will use the equation mod equals to 2 in the power of n, and then we will use log to simplify the question, and then we will get the number of flip-flop that will be used. And the second one, we will draw the state of diagram. The third one, we will construct the table. So the fourth one is we will have to draw the counter circuit and timing diagram by based on the table that we construct just now. So next, we also have the design asynchronous counter in 3-bit, which have up counter and down counter like usual. So how to design? We we can design asynchronous counter in 3-bit the same with 2-bit. So first we determine the number of flip-flop, use log uh, in the equation, and then the second one is draw the state diagram, and the third one is construct the state table. So the last one we have to draw the counter circuit and timing diagram. So we have to draw a counter circuit based on the construct table, and as we can see in the timing diagram, uh, the timing diagram is in negative edge triggered because when clock changes from high to low, high which is 1 and low is 0, the Q0, Q1 and Q2 will changes. So this is the simulation timing diagram for asynchronous counter. We use 2-bit because there is 2 flip-flop as you can see in the multisim that we use. So now we move to synchronous counter. So what is synchronous counter? Synchronous counter is when there is no connection between output of first flip-flop and clock of next flip-flop. So the flip-flop are clocked simultaneously. So the third one is circuit becomes complicated as number of states increase. The fourth one is speed is high as clock is given at the same time. So as we can see, there is different with the asynchronous counter at the clock connection. So this is the design of asynchronous counter in 2-bit. So it is the same with asynchronous counter, which have down counter and up counter. So the connection of down counter and up counter only difference in the Q bar and Q at both flip-flop. So now I will explain how to design. It is the same with asynchronous counter 2-bit and 3-bit that we know. First, we have to determine the number of flip used. Second, draw the state of diagram. Third, construct the state table. So the last one is the most important, which is we need to draw the counter circuit and timing diagram based on the construct table. So this is the design of asynchronous counter in 3-bit, which we have down counter and up counter. So as you can see, the clock is connected simultaneously, and the connection of uh, Q and Q bar is different for up counter and down counter. So this is the simulation timing diagram in synchronous counter. So here we have 4 bit because we have 4 flip-flop in the timing diagram. So in conclusion, sequential logic circuits are important in digital system because they store and process data using latch, flip-flops, and counters. They are widely used in registers, timers, and computer systems. That's all from our group. Thank you.